Avalon Mark 3.5 is TJUAV's second submission to the AUVSI SUAS competition in 2022. An original design built by 20 high school students from Thomas Jefferson High School for Science and Technology, Avalon boasts a Pixhawk for autonomous flight, an unmanned ground vehicle, and a camera gimbal, among other electronics and features.
Here is a picture of our team consisting of 15 members led by co-presidents Ari Bobesh and Liam West.
Here is a recent picture of the team at the field. The fuselage of Avalon Mark 3.5 consists of a 3D printed nose cone, tail cone, and bulkheads clamped to an 8-foot aluminum spar. The bulkheads have slots for foam paneling, and the individual component bays allow for maximum modularity. The wing consists of 2 aluminum spars that span the laser-cut plywood ribbon truss structure covered by DocuLam, a laminate covering. The wing attaches to the fuselage spar with a 3D printed clamp, and separate aileron sections slide onto the wing spars and bolt to the main wing. The plane is supported by a double-wheel landing gear at the front and an omnidirectional wheel at the back. All electronic components are mounted to a vertical plywood wall in the designated electronics bay. The compartment for the UGV, Unmanned Ground Vehicle, has an open bottom so that the vehicle can exit the plane when the servo release mechanism is actuated. The UGV itself is 3D printed and contains the Pixhawk Mini, GPS and antenna, servos, power module, 3S battery, and water bottle. Lastly, the tail section, including the left and right elevators and the rudder, utilizes the same plywood ribbon truss structure with added wooden dowels for rudder support.
The aircraft uses a Pixhawk 2.4.8 flight computer for autopilot, with an RFD 900X radio for telemetry. A 2.4 GHz RC receiver connects to the Pixhawk through S-Bus for manual control. A Raspberry Pi 4 captures images from a C3 cam camera and sends data to the ground station using a Ubiquiti Bullet M2 through a 2.4G Wi-Fi link. A self-stabilizing gimbal keeps the camera level and in the same compass direction to aid in image processing. The aircraft's 2 motors are powered by 2 6-cell 16 amp-hour lithium polymer batteries in series. All other electronics are powered by a separate 4-cell 5 amp-hour battery.
TJUAV's custom-built ground station was designed as a hub of both information and control for various aspects of the mission. The flight data page is designed to model Mission Planner, a commercial autopilot ground station. The Quick tab displays basic telemetry data of both the UAV and UGV, and the Actions tab allows quick control over the 2 vehicles, including arming, setting flight modes, and adjusting missions. The Map tab is designed to help the team with customizing and validating a flight path for the competition, and will mostly not be touched during the mission demonstration. Logs tab provides a live feed of logs from both the TJUAV ground station and the onboard Pixhawk flight computer to help monitor the status of the flight and to solve any issues that may arise. Additionally, the Parameters tab is designed to read, edit, and write parameters to and from the onboard Pixhawk. This is also mainly only used pre-flight. The Missions tab provides a live feed of images taken from the plane, which have been processed through our object detection and classification algorithm. When an object has been identified, it will show up in the viewing section of this page. Then, members of the TJUAV team can reject, modify, or submit these objects to the interoperability server for scoring.
TJUAV will be attempting most competition tasks with the Avalon Mark 3.5, including autonomous flight and obstacle avoidance, object detection, classification and localization, and airdrop. TJUAV will not be attempting the mapping task. Following our developmental and mission testing, we have a high confidence in the Avalon Mark 3.5's autonomous flight capabilities and anticipate it will perform as expected at competition. We have a medium confidence in the system's obstacle avoidance capabilities, low confidence in the object detection, classification, and localization task, and medium confidence in the airdrop task. The testing performed on the Avalon Mark 3.5 to achieve these confidence levels were conducted at all levels of the system. Component testing was conducted first, testing various aspects of the system individually, ensuring they would perform properly and were ready for integration. These tests were conducted on static structures to measure loading capabilities, dynamic systems to ensure adequate response and performance, and various mechanisms and computer systems to ensure proper functionality.
In total, we have completed 6 flights in which we switched to autonomous mode. However, we are not attempting autonomous landing or takeoff, and we wanted to thoroughly test the Pixhawk's behavior each flight before switching to autonomous mode. Therefore, we only spent an average of 40% of the flight duration in autonomous mode. To tune the UAV for autonomous flight, the Pixhawk first needs to trim the control surfaces. This is done by entering fly-by-wire mode and centering all inputs, allowing the Pixhawk to adjust the control surface trim values for hands-off level flight. Additionally, for autonomous mode, the PIXHAWK has certain parameters used for PID relating to roll, pitch, and yaw. It's possible to set these manually, but we used AutoTune mode to teach the PIXHAWK these values. In AutoTune mode, we first aggressively roll left and right 20 times, and then pitch up and down quickly 20 times. The PIXHAWK adjusts the PID parameters based on the aircraft's responses to the control surface deflections, giving the PIXHAWK the data it needs to control the plane autonomously.
For competition waypoints, the team will use a script which parses waypoints and creates a path. During development, this script can be tested on many different waypoint sets to determine the robustness of the code. Based on our physical testing with Mission Planner, another ground station, for autonomous waypoints, the plane was able to hit 100% of waypoints within a 25-meter distance, as long as the waypoints were properly distanced. To ensure safety, the waypoints are manually reviewed by a team member before flight. The team has been unable to physically test obstacle avoidance path integration thus far. However, obstacle avoidance need not be physically tested in principle, as it can be tested via running it purely on the computer, using many sets of waypoint paths with obstacles. After a good path is generated, the obstacle avoidance boils down to how well the plane can follow the waypoints, which has been demonstrated to work well in the waypoints performance section.
The C3 cam is a 13 megapixel camera with a 4208 by 3120 resolution. Avalon 3.5 took test images for the past 6 flights, but images were overexposed and slightly out of focus, and many images were at incorrect altitudes due to flight testing. However, according to our testing on the ground against a target with 250-foot separation, which is the intended operating altitude, targets should be about 18 pixels across and are easily classifiable with the correct exposure settings. To ensure correct exposure, the team will attempt to change shutter speed or use polarizing filters.
In order to create realistic data for flight, our algorithms are tested using synthetic data with a variety of backgrounds and target characteristics. Images are first processed with dominant color background removal using k-means. The resulting image is passed through a modified YOLO network, a convolutional neural network designed to detect small objects in aerial data. From there, we crop the targets to conduct further analysis. We use k-means to separate the shape and the letter and extract the color of both. The masks of both the shape and the letter are passed into convolutional neural networks for classification. Furthermore, we use a convolutional neural network to find the orientation of the letters. The YOLO network correctly detects approximately 90% of the targets in the synthetic data. Both the shape and the letter classification networks have an 89% accuracy. Our detection algorithm operates at a high accuracy of 90%, identifying the positions of objects accurately on images. This algorithm was tested on thousands of images with varying backgrounds and target characteristics. The error of our localization algorithm is minimal and dependent on the slight error caused by the GPS and lens distortion.
Although our drop mechanism works as intended and has successfully deployed our UGV during ground testing, our 2 attempted airdrops have been unsuccessful. This first was due to our plastic locking clamp breaking, which was addressed by switching to a metal piece instead. The second was because our parachute strings were cut by the sharp edge of the metal locking clamp, which is being addressed by adding fillets to its edges.
TJUAV also conducted full mission tests, where we attempted all expected competition tasks in a simulated environment. 2 full mission tests were conducted, with manual takeoff, attempted airdrop, transition to autonomous flight mode, image capture, manual takeover, and manual landing. These tests displayed sufficient coverage of core mission goals and showed sufficient safety of the system. From these tests, improvement was made to the UGV deployment mechanism, and more interpolating waypoints were added to flight paths. Additionally, the camera system did not function as planned with the consistency necessary for competition, and there is ongoing development of a solution. In both full mission tests conducted, the team was able to operate within the timeline and with operational excellence. Additionally, all waypoints attempted were captured within a 25-meter accuracy, and the team utilized a manual takeoff and landing. All other competition tasks attempted were not sufficiently completed to earn points. The team hopes to achieve better than this estimate as improvements continue to be made to the system.